Let's try and understand equation of continuity. Now this again is a tube, narrow at the top, broad at the base. Area of cross section is much greater than area of cross section over here. Here we are talking about section RS, and here it is section PQ. Alright, now velocity of fluid moving in this section where the area of cross section is high is low, moves slower, whereas velocity over here is much higher. Now we have seen gardener, okay, gardener when the gardener is watering plants very close to him or herself, keeps the entire mouth of tube open. But whenever the person needs to water plant which is further away, he presses the tip of pipe. Now why does he press the tip of pipe? Why does he press tip of pipe? It's only to make the flow of water move to a longer distance. So when he closes, when the pipe is open, it just falls here. Why does it go much further away than when it was open? It's only because velocity of water increases when the area of cross section decreases. So that's what is mentioned over here. So whenever the area of cross section is small, the velocity of water increases in that section. All right. Now, and this is the length, and this is the length here, L1 of this cross section PQ, and L2 is the length of this section RS. All right. Now let's get into this derivation. Now mass M1, if we talk about mass of fluid entering and leaving section PQ, is equal to mass of fluid entering and leaving section RS. So mass at constant time del T, delta T. So mass at a particular time. Now say, for example, if I say in 2 minutes 1 kg of water flows from here, in 2 minutes even here 1 kg of water would be flowing. So mass of fluid coming out from this section would be equal to mass of fluid coming out from here at a fixed interval del T. All right. So this one thing has to be clear. That's what I mentioned over here. M1 is equal to M2 at constant del T. All right. Now, few things that we know. Rho, that is density, is equal to mass over volume. So mass is equal to rho V, and volume also is equal to A into L. That is area of cross section into length. That becomes the volume. And velocity is equal to L over del T, the time that it takes to travel. That is L over del T. So velocity is equal to L over del T. It is distance over time, right? So here the distance is L and time is del T. So del T. So velocity, if I multiply velocity with del T, what we have is L. So L can also be represented as velocity into del T. Keeping the conversions in mind, let us proceed to derive A1 V1 is equal to A2 V2, where A is area of cross section, V is velocity. So now our contention is M1 is equal to M2. M1, M2. Mass of fluid passing out of this column is equal to mass of fluid passing out through this column, through this section, in fixed time del T. So M1 is equal to M2, M1 is equal to M2. So rho V1 is equal to rho V2. Just to clarify, this is not velocity, this is volume. And volume already we saw is AL. So if it is for this, it is A1 into L1, volume for this V1. And for V2 it is A2 into L2. Here it is V1 is equal to A1 into L1. And here V2 is equal to A2 into L2. So that's what we have mentioned over here. Now we also checked out over here that velocity into delta T is equal to L. How? I have explained here. So instead of that, what we did is instead of L, we wrote velocity into delta t. Instead of L, we wrote velocity into delta t over here. So it is same for both. So rho A1 velocity 1 into delta t is equal to rho A2 velocity 2 into delta t. So all these things gets cancelled. So we find that since it's the same fluid flowing through both the columns, so density is same, so it gets cancelled. Then time is same, del t gets cancelled. So what we are left is area of cross section and velocity. So A1 V1 is equal to A2 V2. So that's the equation of continuity. All right. So equation of continuity, or we can say A1 V1 is equal to A2 V2, or AV is constant. So this itself proves what? Area of cross section is inversely proportional to velocity. Area of cross section is directly proportional to pressure, or rather velocity and pressure are inversely proportional. So whenever velocity of fluid flowing is very high, pressure at that place would be very low. So smaller cross-sectional areas generates higher velocity and lower pressure. Application of this we would see shortly. All right. So this is all about equation of continuity. This is all about equation of continuity. So if we just try to apply it over here, so velocity here would be very high because the area of cross section is very low, and so the pressure experienced also would be very low. All right.